We're trying to determine the energy of activation for a reaction using Arrhenius equation. The problem states that the rate of a reaction where A gives products increases by a factor of 2.41 when the temperature is increased from 31 degrees Celsius to 41 degrees Celsius. What is the activation energy for this reaction in kilojoules? The value of R, the universal gas constant, is given as 8.314 joules per Kelvin per mole. In order to solve this problem, we are going to use Arrhenius equation. Arrhenius equation can be written as K is equals to A into e raised to minus EA by RT. K represents the rate constant at temperature T. A is called frequency factor. It's unique for a given reaction. EA is the energy of activation. R is the universal gas constant. And T is the temperature in Kelvin. In order to solve for the energy of activation, we will first apply the natural logarithms. If you have not yet studied logarithmic functions, you may want to watch a couple of videos on logarithms before you can proceed. Here we are proceeding with the assumption that you are familiar with logarithmic calculations. So in order to lose the exponent, we are going to apply logs. Log K is equals to ln A minus EA by RT. Since we are trying to find the energy of activation for two different temperatures, we're going to rewrite this equation for two different temperatures, T1 and T2. For T1, the equation reduces to ln K1 is equals to ln A minus EA by RT1. And for temperature T2, the equation is going to reduce to ln K2 is equals to ln A minus EA by RT2. So we have two equations, equation 1 and equation 2. In order to calculate the energy of activation, we are going to subtract equation 1 from equation 2. And this is done like this. Ln K2 minus K1 is equals to minus EA by R into 1 by T2 in brackets minus open brackets minus EA by R times 1 by T2 and close the brackets. So we have taken equation 1, equation 2 and subtracted equation 1 from equation 2. Equation 2 has a higher temperature and equation 1 has a lower temperature. Now ln K2 minus ln K1 can be written as ln K2 by K1. We are going to rearrange the equations. On the right side, EA by R into 1 by T1 has a negative sign, and outside the bracket there is a negative sign again. So that makes the term a positive term. So I'm going to rearrange it and write EA by R into 1 by T1, the positive term, minus EA by R into 1 by T2. I've just rearranged it to make the positive term first and the negative term second. Now the common factor EA by R is going to be taken out. And then we will get this equation. Ln K2 by K1 is equals to EA by R into 1 by T1 minus 1 by T2. Since 1 by T1 and 1 by T2 are fractions, we can also rearrange it in order to solve for EA like this. Ln K2 by K1 is equals to EA by R, where T1, T2 is the LCM and T2 minus T1 will give you the difference in temperature. We can further rearrange this equation to solve for energy of activation like this. EA is equals to R into ln K2 by K1 into T1, T2 divided by T2 minus T1. Now, in order to solve for the energy of activation, all we need is this equation. So for the problem given, if you substitute the numbers that were given to you, you should be able to calculate the energy of activation. Now in the problem that was given to you, you were given the ratio of ln K2 by K1 as 2.41 because the reaction doubled, or rather increased 2.41 times when the temperature changed from 31 to 41 degrees Celsius. R was given as 8.314. Initial temperature was 331 degrees Celsius. We're going to convert it into Kelvin. For all calculations, temperature should always be used in Kelvin. So 304.14 Kelvin. And T2 is 41 degrees Celsius or 314.14 Kelvin. Now we can substitute these numbers in the above equation. And this will give you an energy of activation of 69.872 kilojoules. So that's how you can calculate the energy of activation. So all you need is the equation given on the slide. EA is equal to R into ln K2 by K1 into T1 T2 by T2 minus T1. Memorize that one. Substitute the values of K2, K1, T1, T2 and R. You should have the energy of activation. But this problem did illustrate how you can arrive at this equation by using Arrhenius equation and how to rearrange it using the logarithmic function. That's it for now.